Today it's my pleasure to introduce our speaker, who is Thomas Barthel. He is an expert in condensed matter theory and quantum many-body physics. And he did his PhD at RWTH Aachen in Germany, and then he had a few postdoc stays in Berlin, in Paris, in Munich, and in Potsdam. And then he became an assistant professor at Duke University for the past roughly 8 years. And now he is moved to UMD to join me at QLab to study basically NISQ applications on near-term quantum computers and implement quantum many-body physics problems and tensor network methods, and also to build kind of error models for some of these systems. And today he's going to talk about quantum simulation of quantum matter using entanglement renormalization. Before I hand over, I have two announcements. JQI fellows should go to the JQI fellows meeting as after that. And if you would like tea with the speaker, tea for postdocs and students, that's at 4 p.m. in Atlantic 2117. Okay, with that, Thomas.
All right, thank you. Yeah, it's great to be here. Thanks for having me. It's a great place with a lot of accomplished quantum physicists. So it's really nice to hopefully also in the future work together. Yeah, so this whole project, the goal is to simulate condensed matter systems on these small quantum devices we have. And yeah, it came up with like me seeing more and more papers on quantum chemistry. You're probably aware, demonstrations on quantum computers. But yeah, from condensed matter, there was very little due to the reason just that if you put naively sort of a condensed matter system onto a quantum computer, then because they're so small, you have gigantic finite size effects. And if you want to study something like a phase transition or something, you get very little signal. But then, so my background, as Norbert said, is in condensed matter theory, and I was working a lot with tensor network states. And at some point, I realized that these hierarchical tensor networks called MERA states are very well suited for the simulation of condensed matter on quantum computers, and this is what this seminar will be about. Yeah, so first I will explain you sort of a motivation of these MERA tensor networks. So coming from real space renormalization group, this will motivate a variational ansatz, these MERA tensor networks. And on this, you can then build a variational quantum algorithm with some minor tweaks to these tensor networks. And some nice properties that these tensor networks have is, first of all, they're noise resilient. You can simulate actually, if you want, an infinite system on a small quantum device. You can access the thermodynamic limit. We also proved rigorously that there are no barren plateaus for this class of tensor networks, and also slightly larger classes, isometric tensor networks, which include also MPS and tree tensor networks. In benchmark simulations, we established a polynomial quantum advantage compared to the corresponding classical algorithms. And I will also show you some first experimental results on ion trap devices, where we really nicely saw a phase transition with a really sharp onset of the order parameter, and also were, I think for the first time, be able to distinguish different entanglement scalings as you go through the phase diagram crossing quantum phase transition. Okay, so first a bit on motivation, so I don't have to talk too much about why quantum many-body systems are interesting in the seminar, but yeah, very shortly, we have this exponentially big Hilbert space. So for the purpose of this talk, please think about lattice models mostly. So maybe we've already done some tight binding approximation or something. We have this exponentially big Hilbert space, which can lead to emergent phenomena like superconductivity, Bose-Einstein condensation, topological order, and so on. And these might, for example, also help us to build protected quantum computers. Like physics-wise, this leads to quantum phase transitions where we have self-similarity at the critical point, leading to power laws in observables and energy gaps, and hence also to universality. And the focus of, my focus is on these strongly correlated systems. So these are systems where the simple techniques we have break down, like so simple single particle descriptions as in a Fermi gas don't work. Also, like Fermi liquid descriptions may break down. Simple mean field or perturbative approaches don't work, and this roughly is the definition of strongly correlated systems. So we need some more advanced techniques like RG on top of perturbation theory or, for example, these variational approaches like tensor networks. And the main task is just to, for example, or one of the main tasks is to minimize energy expectation values for some state in order to study then the low temperature physics of the systems we are interested in. Okay, if you haven't heard of tensor networks, this is a very short introduction, so please also interrupt me at any point if you have questions. So the basic idea is that if you have no particles on such a lattice, let's say, for example, think of a spin-1/2 system where we have spin up or spin down on every side, then a generic state can always be expanded in the corresponding product basis. So the sigma i's here would be the spin orientation on side I, and then the state is characterized by these expansion coefficients psi. And yeah, so this you can think of this thing you can think of as a big tensor with n indices, and if the local Hilbert space dimension is d here, then we have d to the n elements for our n-side system. Which of course, if you want to use this parameterization, you're dead pretty quickly, right? So maybe you can do 40, maybe up to, with a lot of symmetries, 50 spins 1/2, if you do it exactly. Other than that, you will have to resort to some approximation, and the idea of tensor networks is to chunk down this giant tensor here into a network of smaller tensors. So the simplest incarnation are matrix product states where we assign one tensor to every lattice side. Each tensor has, again, one of these physical indices labeling the local basis state on that side, and then auxiliary indices corresponding to these lines here, which are contracted with corresponding indices of tensors on neighboring sides, in order to then sort of construct this giant tensor or an approximation of this giant tensor. Yeah, so this line here is a sum over common indices, as in the matrix product, hence also the name matrix product state. All right, and we are free to choose the dimension of these auxiliary indices here. We call this the bond dimension chi. And then, yeah, so we've gone from a simulation that is exponentially expansive in the system size to one that is linear in the system size, or at least polynomial in the system size, and also polynomial in this bond dimension chi, because, for example, in these matrix products, these algorithms go as chi to the power of 3, so it's quite benign. Of course, the important question is then, what bond dimension chi do we need, right? So if this chi is exponentially big in the system size, we haven't gained anything, but you can prove for 1D gapped systems, you can show, or more generally, if you have an entanglement area law, that actually the bond dimension for a fixed accuracy that you want to achieve, the bond dimension is independent, that you need is independent of the system size. If you go to critical systems, then the system doesn't obey this entanglement area law anymore, but in the ground state you have the so-called log area law. So you have long-range correlations, like correlation length has diverged. The system is usually described by a conformal field theory. And in this case, turns out that still computation costs are polynomial in the system size, where this exponent is typically pretty small, depends on the central charge of the CFT. Yeah, but then if you put these MPS, this matrix product state, on a 2D lattice, so this is also frequently done, right? So just wrap it in some way onto your 2D system. Then an issue arises because this MPS does not properly reflect entanglement structure of the ground state, right? So for example, in the MPS, these two sides are nearest neighbors, which is fine. So there can be strong correlation, but for example, these two sides are not nearest neighbors in the MPS, but physically they are nearest neighbors. So there will be a lot of correlation between these, but sort of all this information, all this correlation is channeled through this long chain. So actually MPS simulation becomes inefficient in one dimension of the 2D lattice, so scales exponentially in this case in the x extent of our system. And yeah, so due to this problem, different types of tensor networks have been suggested. So MPS came up very early on. Maybe the very important step was one by Steve White, where he invented the DMRG method to optimize such states. And it sort of came with a shock to the condensed matter community that with a very simple algorithm optimizing this MPS, you can get like machine precision ground state properties for non-trivial quantum magnets, 1D quantum magnets. And this was then later on generalized to 2D. So the ideas for the PEPs is very similar. We just assign one tensor to every lattice side, and then we connect these tensors with auxiliary indices. the main topic of today will be these MERA states, so very fancy name, multi-scale entanglement renormalization ansatz, which is motivated by real space RG schemes. So it has this hierarchical structure where basically in the first layer we encode short-range correlations in the system, and then as we go deeper into the hierarchy, we encode longer and longer ranged correlations in the system. And you can do this in 1D as shown here, or in 2D. So we have a sequence of some like unitaries so-called disentanglers, and then isometries which decimate the state space. Okay, this and you can show that, or at least in 1D you can basically rigorously show that this is a good ansatz for many-body ground states. In 2D it's more anecdotal, so we have numerical evidence. These type of states have the right kind of entanglement properties, so it's quite convincing that these states properly parameterize the interesting corner of physical ground states, right? If you're not interested in like arbitrary states in Hilbert space, but just ground states with some locality properties, then typically you can encode them efficiently with these networks. So this is great. A big drawback is that if you go beyond 1D, the computation costs get really large in this bond dimension. So for example, for these PEPs in 2D, the contraction cost, right, you have to contract certain types of networks. Here in PEPs actually already involves some approximation and still scales with the 10th or 12th power in the bond dimension. MERA in 1D is still handleable, so high to the 7, 9 is not nice, but still doable. But then as you go to 2D, it really becomes very awkward, right? So classically, there are basically very, very little papers which like use this in productive sense. There were benchmark work and so on, but at some point, actually, the activity on these 2D MERA kind of died out, also because we proved at some point that they're actually a subclass of PEPs. Okay, and so I'm pursuing 3 different routes to get out of this misery. One is to impose constraints on the tensors. So I don't want to talk much about it, but the basic idea is to impose a constraint on the CP rank of these tensors, and this makes the contractions much more efficient. Another idea is to not use, let's say, use the tensor network and then get the exact energy gradient, do some energy descent algorithm, but to sample, introduce some sampling, so sample energy gradients and energies and so on. This can reduce computation costs quite drastically, but the scaling is not quite clear yet. And what we will talk about today is a hybrid quantum classical algorithm, where we put the tensor network on a quantum computer in order to get rid of these costly classical tensor contractions. Okay, what's now the main idea of these MERA states? So as I already mentioned, the motivation comes from real space renormalization group, as in Kardanov's block spin transformation. So let's say the bottom here is our physical lattice, where each point here corresponds to one, let's say, spin 1/2, for example, or any local finite dimensional quantum degree of freedom. And then we would step by step decimate the state space, right? So for example, you could have some scheme where you like locally solve a ground state problem or solve the energy eigenvalue problem, discard the highest energy states, so decimate the state space, and then continue again, take 2 of these renormalized sites, decimate the state space, and go on until you've come to a small enough system such that you can, for example, solve it exactly. Unfortunately, this approach does work only for very few systems, so basically Ising models. And the reason is that in this graph here, sites that have, so similar to the MPS on 2D, there are sites which are nearest neighbors physically, but in this graph here, they can be quite far away, right? So for example, if you look at these 2 points, they are also nearest neighbors in the graph, in this RG graph, but these 2 sites are nearest neighbors, but they have a large distance in the graph. So this will introduce, can introduce strong errors. And then in 2007, Geoffrey Vidal had the great idea to just modify this in a very simple way, just introduce additional unitary, so-called disentanglers. So the idea of these guys is to, for example, let's say if you look at this guy, to first, so it's a unitary operation on these 2 sites, and the purpose of it is to some extent disentangle this part of the lattice from this part of the lattice. Of course, can only disentangle a little bit, right? But that's the idea, that disentangles a little bit before we do the state decimation. And now you see that in this new graph, any two sides are actually have a maximum graph distance of 1 or 2, right? So this is much more efficient ansatz, and yeah, should work for, we expect, for most quantum many-body systems with some locality features that we're interested in. Okay, yeah, so here we had in this page, this direction was the renormalization direction, right? Now, if you turn this thing around, then we can interpret this also as an ansatz for a many-body state, right? So now we look from the bottom up as a preparation of a many-body state. So just now having these partial isometries which generate from 1 degree of freedom, 2 degrees of freedom. Then we have entanglers which entangle 2 neighboring degrees of freedom, and then we continue the scheme. This prepares just an entangled many-body state. And we can use this as a variational ansatz in order to get approximations, for example, to the ground state. And there are many different variations of this. So the first two, you just have some branching ratio of 2. Here, this guy has fewer tensors in order to reduce the classical computation costs. You can also do ternary MERA. You can do this in any number of spatial dimensions. So here's some examples for 2D mirrors, where you again have some disentanglers and then isometries, which, first the isometries and then some disentanglers. And then you repeat the step going up, sort of, let's say, in this direction here. Okay, and yeah, some basic properties of this MERA. First, they have some nice, as I mentioned, some nice entanglement properties. This we can notice if you, for example, ask about the entanglement of some subregion of linear size L with the rest of the system. Then we can, first of all, the simplest thing is to bound how much entanglement we can have at most, right? And to determine this, we just draw some minimal surface here through the tensor network, cutting as few auxiliary indices as possible to get to the other side. And then we just count, we count how many of these contraction lines here we cut. This will give us a bound on the maximum rank of the reduced density matrix for the subsystem, and hence a bound on the maximum entanglement we can have. In 1D, you see that in every layer we cut one contraction line on every side. So we just have to add up here 2 to 2 for each of these layers. For the minimal surface, this goes into the depth log L. And so the total entanglement is log L, which is exactly the entanglement scaling that you have in critical 1D systems. For 2D, you basically sum up a geometric series and you get the so-called area law for entanglement entropies. So the type of entanglement that you would expect for gapped 2D systems, which means that probably if you simulate a 2D system with MERA, at a critical point, you will probably still need to increase the spawn dimension chi if you go to the critical point. But it should be polynomial, so not too bad. Okay, so we have to write the entanglement properties. Yeah, as I mentioned, actually for 2D and higher dimensions, these MERA form a certain subclass of PEPs, which has some nice properties. So you can evaluate observables. In contrast to PEPs, you can evaluate observables without approximations. And what we also realized quite some years ago is that also these tensor networks have no sign problems. So the big competitor to these tensor network approaches is quantum Monte Carlo. But for fermionic systems or also ferrostatic magnets, quantum Monte Carlo has typically this negative sign problem where the sampling becomes exponentially inefficient. And here in these tensor networks, you can take care of the anti-symmetrization without with just a marginal overhead. So there's no sign problem. Okay, so how do we put this now on the quantum computer? First of all, so I claimed that with a MERA on a quantum computer, we can simulate basically infinite size systems, although we just have maybe 20 qubits or something, right? And this is the explanation here how we can achieve this. So the lower part is again our MERA tensor network, so the state that we prepare going from the bottom up. And what this entire graph here represents is the expectation value of this local expectation, the expectation value of a local observable. That's a local observable HI here is, for example, a Hamiltonian term which acts in this case on two sides. And if you want to just evaluate the expectation value with respect to the MERA psi. So we have our cap psi here at the bottom, and then the bra psi at the top, which is just the reflected tensor network. And then we have to, in order to do this multiplication, we have to do these contraction lines. Okay, and what now comes to help us, where did I put this? Sorry, put this here. So what helps us now is that I told you these guys here are unitaries. So if you call this unitary U and this U dagger, then what we have here is nothing but the product U dagger U, which is called identity. So we can just remove these two guys and do the contraction from this blue corner here to this blue corner right away. We can remove these green tensors. And then if you've removed all these green tensors here, then we have here contraction of this blue isometry with this blue isometry. They are isometric. So again, we have something like V dagger V with these isometries also gives identity. So we can just as well remove these two isometries. And then you can continue, and it turns out that everything outside the so-called causal cone, this bluish region here, the causal cone of this local observable, can be removed. And we get a drastically simplified tensor network, which looks like this here. And you see, like in every layer, we just have the same number of tensors. And you see also some contraction lines which leave the causal cone here. So everything that's red here are contraction lines which leave the causal cone and go up here. And on a quantum computer, this could be qubits that we measure, reset, and then reuse in order to implement the next isometry here. Okay, so this is how we can simulate very large systems on small devices, right? So the number of qubits you need is basically proportional to the number of black contraction lines here in each of these layers. And then, yeah, for the unitaries and isometries, in principle, you could implement them directly, but that's quite expensive. So what we suggest is to approximate them by a so-called, by a brick wall circuit, which you also call Trotter circuit, because at some point these unitaries actually get close to identity. And so we just alternate on the bonds here, acting with 2 qubit gates. And then the question is maybe how many of these Trotter steps T do we need in order to get an accurate approximation? So we have this additional parameter now, small t. Right? So the parameters we have now is the number of MERA layers, that's this capital T, which corresponds to log the system size. We have the small t, which is the number of Trotter steps for each of these MERA tensors. And we have the bond dimension chi, which is now related. If you put this on a quantum computer, we implement each of these renormalized sites of dimension chi, Hilbert space dimension chi, by q qubits. Yeah. So in this case here, we had bond dimension 16, for example, and then we implement this by using 4 qubits. So q is equal 4 in this case. All right. Yeah. So then there are no complex tensor contractions anymore, right? We just have this. We just implement this quantum circuit, and so the computation time just scales linear in the number of layers and in the number of Trotter steps t. And if you go through the numbers, turns out that the resource requirements are quite doable. So let's say we have a 1D MERA with bond dimension chi equal 8, so 3 qubits per renormalized sites, 6 layers, and 2 Trotter steps for each of these tensors. Then you will need either 12 qubits and circuit depth 120 if you minimize the qubit count. If you minimize for circuit depth, you will need 18 qubits and circuit depth 48. And also the requirements for 2D seem quite reasonable. So if you have here bond dimension chi equal 4 in 2D, 6 layers, 2 Trotter steps per tensor, then you can get away with just 28 qubits, circuit depth 624, which is maybe a bit big yet. But if you optimize for circuit depth, then you go down to 96. So it's still that looks doable now or maybe in the near future. Okay, and yeah, so if you can evaluate expectation values, we can also determine gradients. So either you can do a stochastic gradient descent, or you can also evaluate energy gradients just by evaluating energies with shifted rotation angles in our quantum gates here. So it's a parameter shift rule, and then do some gradient-based optimization like LBFGS or some version of that. Yeah, so there's one caveat, and that's I didn't talk about. So here I just talked about like one local energy term, right? One interaction term. If you now have an extensive Hamiltonian, so your sum of many local interaction terms, then how do we get the sum over the system size, right? But if you have a translation-invariant system, it turns out that you can do this very efficiently. So let's say we have such translation-invariant Hamiltonian, and we want to evaluate the energy expectation value for each local term on every possible bond here. So we have to run sort of through all these guys. We have different corresponding causal cones. But these causal cones are actually, the structure just consists of two components. So it's just any sequence of these two different layer transition maps, right? So either you apply two disentanglers, then apply three isometries, and you either trace out one side on the left and two on the right, or vice versa. And for any bond, sort of you have a specific sequence of these left and right moving layer transition maps. So if you want to sum over all sides here, we just have to sum over all possible sequences of these layer transition maps. And this you can do efficiently also in a quantum computer just by implementing sort of the convex combination of these two channels. And this way you get the energy density in one go, basically. All right, here's some first benchmark data. Yep. Yeah.
Do you have a scaling function? So you said it's like the classical was like high to like 7 to 9.
Yeah.
Like that, or what did you have like a?
Yeah, this will come in a minute. Yeah, very good question. Yeah, that's of course a decisive question, right? Okay, here's just the first calculation or demonstration concerning like what bond dimension do we need with these trotterized mirrors. The simplest model you can think of, the transverse Ising chain, which as a function of this transverse field here has a phase transition from the ferromagnetic phase to a paramagnetic phase, where the symmetry, the Z2 symmetry is broken in the ferromagnetic phase. And yeah, this is basically data here as we scan through the phase diagram. So G=1 is the critical point. And you see the accuracy and the energy density compared to the exact one we get for different mirrors. So this here is a full mirror where we don't trotterize the tensor. This is with bond dimension 8 and 6 layers, and you get like 10 to the minus 5 accuracy. So that's in the worst case at the critical point, which is good enough for most purposes. And we can get very similar accuracy if we add this trotterization. So if you know approximate this tensor by this brick wall circuit, even with just 2 trotter steps, we get very good results. And yeah, these curves here show the convergence as a function of the number of iterations, like energy minimization steps that you do. Okay, now the question, exactly your question, what about the computation costs? So we want to compare the classical to the quantum computation cost, which is not so trivial. Yeah, so what are the costs in the quantum case? We already talked about that. To evaluate a local, the energy density, basically, you need small t times capital T time, right? Number of layers times number of trotter steps. Now, also the number of, sorry, this was this here. Then also the number of total number of gates we have is also proportional to T times capital T. So if you want to get the energy gradient for all of these trotter gates here, then the cost will be T squared. Then, of course, additionally, we don't get the energy expectation value right away, right? We can just sample the energy, so we get discrete results, and our energy accuracy will go then as 1 over square root of number of samples that we invest. And this translates, if you want to achieve energy accuracy epsilon, then this translates into the total quantum cost being this here, right? So this T squared divided by epsilon squared. You can reduce this epsilon squared by 1 power if you use quantum amplitude estimation, which means, but also comes along with deeper circuits and more qubits needed. Okay, but for now we use this the scaling expression for the quantum cost to compare to the classical algorithms. And here are some examples for different SU2 symmetric spin chains. Right, so we have, for example, this spin one, as the most general SU2 symmetric spin one chain with nearest neighbor interactions. Then also these spin 3/2 chains, either this with bicubic bicubic, bilinear, biquadratic terms, and then we also have the isotropic Heisenberg antiferromagnet. And in all cases, what the plots show here is, as a function of the cost, so this could be the quantum or the classical cost, we show the energy accuracy that is achieved, right? Of course, the energy accuracy should improve as we invest more resources. And this black line here, this is the classical computation cost, so it pretty well follows the power law, the energy accuracy. And these curves here are for these trotterized MERA, where the different colors correspond to a different number of trotter steps. So what basically happens is you go down according to power law, and at some point, you can't get further with the same number of trotter steps for each tensor, and so you should switch to a larger T, use more trotter steps, and then, but if you do this optimal, you will also follow power law, and you see in all these plots that you have some at least small polynomial advantage already in 1D, but we expect that in 2D, the advantage will be much more drastic because just the computation cost increased so drastically, the classical contraction cost increased so drastically if you go to 2D or even 3D. Yeah.
Okay. So what's being varied along? I mean, the cost
is
determined by some parameter from the previous plots.
Yeah, exactly. Yeah. So for the classical simulation, the only parameter is the bond dimension chi. So each dot here corresponds to increasing chi, I think, by 1. And then we plot this like chi to the power of 7 or 8, depending on what it is, right, for the given MERA. And for the quantum cost, we have this formula. So we can, so for a fixed color, so the capital T is just something that's big enough. For a fixed color, this number of trotter steps, so the number of layers in the brick wall here, it's fixed. And then what we vary is the number of qubits per normalized site, which correspond to the bond dimension, right? So bond dimension is 2 to the power of q. Yeah. So that's varied for the quantum case. And then at some point we have to increase the number of trotter steps to get further, right? And so we going from blue to red, we increase T, and then from red to red dot, we again increase Q. So more and more qubits per normalized site.
Because the top panel A has the legend triangle is Q equals 3 and blue cross is Q equals 2. So that...
Oh, sorry. Yeah, I was explaining this wrong. Sorry. Yeah, very good. Oh, sorry. Yeah. So along the, yeah, you're absolutely right. So along the, yeah. So I'm just sorry. So along the for fixed color, Q is fixed, number of qubits per noise site, but T is varied. The trotter step. So trotter step increases 1, 2, 3, and so on. And then, yeah, sorry. At some point, increasing trotter step doesn't help. You should use larger bond dimension, but you also see that this nicely converges here to the chi equal 2, chi equal 3. No, sorry, this is actually chi equal 4, right? So this would be the chi equal 4 value, and this guy converges to the, this would be chi equal 8 value, exactly. Yeah. Okay, excellent question. Okay, so yeah, no, to compare the computation costs is actually not so trivial, especially in gapped systems, because in gapped systems, basically the prefactors in your scaling would dominate. But for critical systems, you find that the energy accuracy is actually improves according to the power law and the bond dimension, and we can determine these exponents better here, these critical exponents better. And at the critical point, it turns out that the optimal number of trotter steps also follows the power law and the bond dimension. And so for these models, we've determined these coefficients here, these exponents, these critical exponents, beta and p. And then you can draw sort of algorithmic phase diagrams. So as a function of the scaling exponent for the optimal number of trotter steps and the scaling exponent of the energy accuracy, you can draw now, you can say, okay, which algorithm, classical algorithm is the best, and where does your actual model sit, right? So we've considered different classical algorithms in these plots here. So the traditional one is this here. So using sort of a non-Trotterized tensors and exact energy gradients. So this was what was used by Giffrey-Vidal. But you can also consider Trotterizing the tensors. So this would be these green parts. So imposing the substructure, and which can be more efficient at small p, right? And then you can also consider not using exact energy gradients, but sampling the energy gradients, so doing Monte Carlo. And this will be beneficial if you have small beta, so small exponents here in the energy scaling. Okay, so we get these fancy classical phase diagrams. The question is now, where does the quantum algorithm sit? And if you go at this one, you see that it completely dominates these algorithmic phase diagrams. So all these, or most of the models that we considered, sit here in Bondi, already sit in the region where the quantum algorithm should have the best scaling. Some sit directly at the border. These are the spin 1/2 systems. And then in 2D, I even had to expand the axis here to still see something of the classical algorithms. So in 2D, we expect that the quantum algorithm should dominate, at least in the regime of large bond dimensions, of course. Okay, yeah, let me show some first experiments that we did at the Duke Quantum Center with Marco Cettina and Ken Brown to test this. So yeah, I don't have to talk here a lot about ion trap systems. So these are turbulent ion systems, which encode the spin degree of freedom in two hyperfine ground states. Again, we used the simplest, again, the Strongly-correlated model, the simplest model that you can maybe think of, which has a nice phase transition. So we have local Hilbert space dimension 2. In this case, we also used local bond dimension chi equal 2. But what you see is, so what is plotted here is the order parameters, so the Z magnetization as a function of our transverse field G. And you see a really nice onset here of the order parameter. Actually, we have a few more points, which I didn't have in this plot. So we can actually also made a logarithmic plot of the order parameter, and you can nicely extract the critical exponent of the order parameter, which I think wasn't done before, couldn't be done before on quantum computers. And you also see a nice agreement. So the dots and these arrow bars, these are for the experiment. And then these shaded regions, these are like simulations according to the noise model, which is 95. So this is showing the 95% percentile confidence percentile region. And you get, similar accuracies, not only in order parameter, but also other observables and local correlation function. So this seems to work quite nicely. And then next step, we also wanted to determine fidelities and entanglement entropies. In particular, we wanted to show to demonstrate this difference of different entanglement scaling at the critical point and away from the critical point. So for example, if you look at entanglement entropy for a bipartition into subsystem A and subsystem B, where the subsystem B here has a linear size LB, then the definition is such that you take the ground state, you trace out the subsystem A to get the reduced density operator of subsystem B, and then you evaluate the entropy function for this reduced state, and this gives you the entanglement entropy. And in this model, we get at the critical point this logarithmic scaling, so-called log area law, whereas away from criticality, the entanglement will saturate as a function of LB to a value that is determined by the correlation length in the system. Okay. Yeah, so the question is like, how do you get, if you want to really do this, literally get the reduced density matrix? In principle, you would have to do tomography on these two sites, on all these sites in subsystem B. So you could do this maybe for 6 sites at most or something. But yeah, so I came up with a nice scheme to do it much more efficiently. So it turns out in the MERA states, you can forget about all these tensors which are outside the causal cone of the boundary. So this here is the causal cone of the boundary between subsystems A and B. And everything outside this causal cone you can remove because we have this trace over A here. Right? So these tensors cancel with the corresponding U dagger on the other side. And also everything that's inside here. So this is some unitary transformation on the subsystem. So if you are just interested in unitary invariant properties like the entropy or fidelities, you can also discard all these tensors inside here. And the only thing that you will have to measure are the sites at the boundary of the causal cone. So you can do this very efficiently. And here the first plot is for the fidelity of the subsystem state. So this is actually the number of layers, which corresponds basically to the logarithm of the subsystem size of the size of subsystem B. And you see that we get fidelities ranging from 10 to the minus 4 to 10 to the minus 2, both at the critical and non-critical points. So very high fidelities compared to experiments where you use a naive, let's say, implementation of the model. They basically assign one physical site to one qubit. There you wouldn't be able to reach this level of fidelity. And here these plots show the different entanglement scaling. So this is for the ReNU2 entropy actually. And you see this linear scaling here corresponds, because this is basically a logarithmic scale, corresponds to this log scaling at the critical point. And away from criticality, you saturate to constant value corresponding to this area law. We can also, if you want to scale this up, either going to larger system sizes or higher dimensions, we can also use the so-called replica trick in order to avoid having to do tomography. And I should also mention that Continuum also has done a very nice experiment with this MERA already, where they measured the critical correlations in a spin chain. Okay, so I have 2 more points. One is on the noise resilience. So it turns out that the MERA are quite resilient with respect to noise, which is, of course, super helpful. So how to see this? So let's say we have, so I talked to you about previously about these layer transition maps. So inside the causal cone, we have a sequence of either sort of a left-moving or a right-moving transition map, and the specific sequence depends on where we sit here in the lattice, right? So in this case, we first have the, I guess that's the left-moving map. No, sorry, that's the right-moving map, then the left-moving, and so on. So we have this the sequence. If you want to take the average over the total system size, I told you we can just implement the convex combination of these 2 channels. So this is what we implement on a quantum computer. And of course, the quantum computer has some noise, some errors. So let's assume that we have now a noisy channel, m tilde instead of the exact one, m. But we have some promise on the accuracy, epsilon, that we still get. Thanks to the fact that this is still a valid quantum channel, we can still remove everything that's outside the causal cone, and we still have, so still the noisy implementation is still variational. So we can sort of, although we have noise, we still can trust results. And we can also bound the error that we do. And the simplest case, what you can do is just expand this in a telescope sum, and you would get sort of epsilon error times the number of layers we have in the MERA. So the error just grows, in this case, logarithmically in the system size, which already is good, but actually this bound is too pessimistic, because if you have a non-critical system, so if you have an energy gap in the system, then the system also has finite correlation lengths, and you can actually choose the maximum bond dimension, the maximum number of layers here. You can actually choose system size independent, because like beyond some point, there are no correlations in the system. And so the error would just be linear and epsilon. There would be no dependence at all on the system size. And then in critical systems, it turns out that if you play the same game, then you end up adding here a geometric series, because it turns out that these layer transition maps are gapped. So they have one eigenvalue 1, of course, but then the second eigenvalue is necessarily smaller than 1. And if you call this lambda, then you get this geometric series in lambda to the power of t, let's say. And so again, the error bound turns out to be system size independent. Okay, I should mention that this is actually was first realized by Isaac Kim and Brian Swingle for MERA. Okay, then another question you may have is, what about barren plateaus? And we were able to prove that these MERA don't have barren plateaus. First of all, what is a barren plateau? So it's a phenomenon that if you have an unstructured quantum circuit, let's say just a brick wall circuit, that in general, the energy gradients or the amplitude of energy gradients decays exponentially in the system size. So which means that you basically try to optimize on a more or less flat energy landscape, right? So the average energy gradient amplitude is exponentially small, then you end up, because we also have a finite accuracy for the energy and energy gradients, you basically end up doing a random walk on this flat landscape and don't get anywhere. But turns out that for MERA and also other isometric tensor networks, so also MPS and these tree tensor networks are also isometric tensor networks. For these, we were able to prove that the average gradient amplitudes just scale polynomial in the one-dimension chi and are system size independent. And we actually worked out the actual scaling of these gradient amplitudes. They also depend on sort of in what layer you optimize, and this information you can also use to improve your optimization and initialization schemes for the optimization. So here are some detailed results, which maybe we can more or less skip. So this is just to mention sort of how we prove this. So we prove this using Riemannian gradients and then just use time measure averages, so implemented through Weingarten formulas to evaluate the variance of the energy gradient with respect to some tensor here. If you do this for these brick-wall circuits, you find that, okay, the average gradient amplitude goes on exponentially in your system size L here. Matrix product states this leading term is independent of L and depends as decays 1 over chi squared, so one dimension chi squared. These are some finite size corrections here, which you can basically ignore. And then if you go to MERA, we again get that the leading term is independent of the system size, which is sort of constant the number of layers. And there's some exponential dependence on the layer index tau here. So this means that the energy gradient is more sensitive to tensors which are at low layers, so small tau, whereas it's less sensitive to tensors which encode the more longer range correlations, which is also quite intuitive. So this suggests that maybe if you optimize, you first want to optimize with respect to the lower tensors and then going up in the network. Okay, and we proved this quite generally. And we also use this information about the specific scaling. For example, if you optimize the MERA layer by layer, so here we first optimize just in the first layer, then we optimize simultaneously in layers 1 and 2, then we switch on layer 3, layer 4, and so on. In the end, we optimize everything in parallel. And it turns out if you do this, you converge with much better convergence, as you also have less cases which are stuck in local minima compared to the naive optimization. Okay, and this already brings me to the conclusion. So so I motivated these MERA tensor networks as a good ansatz to study strongly-correlated condensed matter systems. We can do these simulations classically, either with exact energy gradients or importance sampling. But we talked about how we can implement this efficiently on the quantum computer. For one, the tensors are already unitary, so it's very natural to implement them on the quantum computer. And also we have this causal structure in the MERA, which allows us to simulate large systems on small quantum devices. The number of qubits is system size independent, and we at least in benchmark simulations we get this polynomial quantum advantage. We talked about some first experiments, the noise resilience, and the fact that there are no barren plateaus in these type of tensor networks. Okay, for the students, if you're interested to work either on tensor networks to simulate quantum device systems on quantum devices, do either numerics or tensor networks also on quantum computers, or if you're interested in open quantum systems, maybe driven dissipative phase transitions, please shoot me an email. We're looking for good PhD students, or you could also write to Norbert, of course. And with this, I would like to thank you for attention.
Questions?
Yeah.
So kind of not like science question, but like how many qubits, like how many error-corrected qubits, or how much depth would you need to like write an interesting paper? Like how many do you need to like get a result if you actually like want rather than sort of a demonstration?
Yeah, so I think like if you want to do something really cool, you would have to go to 2D. Somewhere at the numbers. Yeah. So here's an example for a 2D mirror. With one dimension calculus 4, you can already. That's already the.
But that I could do on the computer, right? Like
but not very well. It's a very super hard. So actually, like classical simulations went up to chi=8,
okay.
and that's about it. And this already involved further approximations. So because the scaling, as I said, it's in one case chi⁻26 or something, right? So it's that's so expensive that you're very limited. And then yeah, 6 layers, two Trotter steps should be enough. So yeah, if you have, I mean, I think the circuit depth is a bit too much currently, but 28 qubits we certainly have. Yeah, and depth 96 I think should be at the range of what we can do. And this doesn't require error-corrected qubits. So this can be physical qubits. 72 I think is a real number. I think with this you could already do certain things already that you can't do classically, because classically you can do the energy optimization, but for example, you don't have easy access on entanglement, for example, in the MERA. So this is like with this, this idea that I presented on getting entanglement, you could already do stuff that you couldn't do on a classic computer. Yeah. And then of course, yeah, if you start simulating strongly-correlated systems, there are many things like phosphorescent magnets you all know, which are very interesting.
You talked about it being k-local extensible to like a k-local Hamiltonian, and does it sort of, how good or bad is that?
Yeah, so so classically, it's also do classically, but it's quite it's expensive because we then get 2 causal cones, right? So if you k-local interactions, so we'd have an interaction term, for example, acts here and somewhere here. Then you would have these. The total causal cone would consist of 2 of these cones, which at some point merge. And at the point where they merge, you get extra costs. Classically, on a quantum computer, it would just mean that you would need more qubits because you also need to implement these 2 causal cones. So more or less, like if you have 2 local interactions, for example, arbitrary range, you would need more or less twice the number of qubits that you need for a local system. Yeah.
There being any advantage, and you know that the interactions fall off with this is according to some power.
You could of course cut it off, yeah. Cut off the interaction at some point. Also, like in many condensed matter systems, like these long range interactions are either like G irrelevant, right, or so not really relevant to see the right physics. So it's maybe not the first thing I would look at, but there may be of course some models where it's interesting. And I think it's doable, but more expensive. Yeah.
Going back to that question of comparison with 2D systems, classical versus quantum. Okay, my understanding was that for many condensed matter systems, and I'm just thinking, let's say that quantum Hall simulations that Mike Zalto is doing, they seem to prefer just doing MPS on a cylinder instead of doing MERA. So when you're comparing, so how would you quantum MERA compare with that? Actually, I don't quite also completely understand why metric products take this preferred over MERA. I just hear it better.
Yeah, maybe let's answer this question first. It's an excellent question. It's kind of embarrassing actually the answer because like as I pointed out, if you put the MPS in this way on a 2D lattice, the cost will scale exponentially in 1 dimension. So what people do is use cylinders, right? And then the cost will be exponentially big so 1 dimension is fine, right? So like the extent in this direction is fine. You can make this basically arbitrarily big, but then extending in this direction or like making your cylinder bigger and bigger, this is sort of with an exponential cost. So why do people still do it? The reason is just that the algorithms for 2D are just so much more expensive, right? So for the MPS, we get here 1 dimension power of 3, whereas as soon as you do PEPs, so PEPs would be classically, I think, is the next best thing you can do. You have chi to the power of 10 or 12, depending on the details of the network. And so even if you're like so right now we're still sitting somewhere at the edge where like this having the wrong entanglement properties, so corresponding needing very large chi, but the big difference in exponents still lets this guy win. But at some point, there will be a crossover, definitely. So at some point, PEPs will win. If you get more computational power, PEPs will win in the classical computations. In the quantum computation, in the MERA, the answer is the same. So we again have these. So we use MPS for 2D because just these computation costs are so high. We're very limited in the chi we can achieve in 2D on the classical computation. But then that's sort of the idea of like put this on a quantum computer, get rid of these very costly contractions of high-dimensional tensors in order to have this MERA scaling much better than the MPS could do at some point.
So maybe if I just put it in terms of what you said in the context of systems, I guess the quantum Hall simulations I'm thinking of, they're mostly gaps. So the correlation links are probably short. So you can get away with a narrow cylinder.
I mean, still, even though it's gapped, you still get this exponential cost. Like the critical thing would of course even worsen the situation, but
on the correlation link, presumably if you have a cylinder that's where
exactly.
If you want to get near a critical system, then that'd be okay.
Excellent question.
Thanks. So you mentioned that perhaps is it like polynomial contraction? Isn't it sort of in general exponentially hard to contract the PEPs? Are there special properties that make you do this? Like Frank came here, give a talk, he said the same thing. Like what? Frank, come on.
Yeah. It's actually not true. So you're right. The cost is exponential because if you, in principle, it's exponential, right? So if you take this PEPs and you want to just evaluate the local expectation value, so we flange the bra on top, so we get this 2D tensor networks without any open indices. So you can imagine these errors being done, and now you have to contract this tensor network. If you start in one corner, let's say we start here, start contracting, let's say at some point we've contracted these 4 tensors, so we have now an object which has these 1, 2, 3, 4 open indices. And if you contract for the tensor, at some point you have to cross a point where in your memory you have a tensor with a number of indices which is proportional to linear size of the system. So it's exponentially in the size. But so that's not what we do. What we do is we contract. The contraction for the PEPs already involves some approximation. So what you do is you take this 2D tensor network and you treat. So again, ignore now these open errors. We can treat this lowest, like in the simplest inclination, we can treat this lowest row here as an MPS, and then we treat this here as an operator, as a matrix product operator, which you can apply to this so-called boundary MPS. And then once you've applied this row to this first row, we have again an MPS, but with a larger bond dimension. We truncate this bond dimension, and then we continue along this direction until we've converged to the steady state of this sort of transition matrix here, and then we contract from the top, and that's it. But you're already involved because you have to truncate. You already have do an approximation in the evaluation of the energy or energy gradient. So what can happen is really that your algorithm becomes unstable. Like if shit hits the fan, then okay, you get sort of an oscillation maybe between 2 different things or something unstable. Also, you can show that. So I have a paper with mathematicians which shows that the set of tensor networks is actually, as soon as you have loops, the set is not closed. So you could happen that the optimal tensor network for the ground state sits at the edge of this of the set, and this would mean that if you converge to that point, that elements of the tensors diverge. So that's another like awkward thing about the PEPs. So I'm not the biggest fan of PEPs, but they're still practical. So
The states you get somehow usually works. But somehow you can prove that.
You can like construct examples where it doesn't work, and the question is how physical are these examples?
All right, maybe we can leave further discussion to the lunch break. And let's thank Thomas again.
Thank you.